So in the previous videos, we've been getting an intuition for vectors in the plane, but now in multivariable calculus, we're most likely going to be dealing in 3 dimensions. So now it's time to level up and go to 3 dimensions instead of 2. So vectors in space now. Now, when I say the word space, that means I have 3 degrees of freedom here. I have an x-axis, I have a y-axis, and I have a z-axis. So far in your math career so far, you've probably just been dealing with just this plane, the x and y plane. Now we're just adding another axis here that's going out of the plane. Usually, in say your algebra classes, you would have been dealing with the x and y plane like this. You were looking down from this way. If I was to draw an eyeball like this, and you were just looking down upon the xy plane from the vantage point of the z-axis. So the z-axis would have been coming out of view right over here. So we're going to get more of an intuition now for working in 3 dimensions. And I promise you, it sounds difficult, but you'll get used to it really fast. So let me just delete my eyeball over here. And this guy, oops, not all of it. I promise you I'll get used to this software very soon. All right. So let's say I have now a point. I want to plot the point P. I want to plot the point P. And it has the point 1, 0, no, not 0 actually. 1, 3, 4. So looking at this, I know that this is the x coordinate, this is the y coordinate, and this is the z coordinate. So knowing this, I'm going to go travel 1 unit along the x-axis, 3 units along the y, and then 4 units along the z. So let's do that. Here, 1 unit along the x, 1, 2, 3 units along the y, and then 1, 2, 3, 4. So this would be over here, but I would have to draw a line going down to over here. So I know how it looks physically in space. I know that it's over here, not just like on these x and z axis, but this would be the point P. Now let's say I have another point. Let's say this is the point -2, -3, -1, and you can see what point I'm trying to drive home here. So now we have to deal with the negative x-axis. So I'd have to extend this axis to the left like this. This is the negative x-axis. The negative y-axis goes behind the plane like this, and the negative z-axis goes downwards like this. So now, hopefully that you see this in your mind. This is supposed to be coming out of the page. And let's plot this now. So this is let me just write this real quick. Negative z, negative x, and negative y. All right, so go ahead, try and do this one. So now we're gonna go 2 along the negative x-axis, 1, 2, 3 along the negative y, and 1 down along the negative z. So let's do it. 1, 2, 1, 2, 3. So we're back here now, and then we're gonna go down 1 on over here. And now I'd have to draw lines going upwards. So I know that it's below this point. It's over here. This one's a little bit harder to visualize, but look up a 3-dimensional graphing software, and if you want, and plot these 2 points and just get a feel for them. So there's one thing that's good about 3-dimensional space and any dimensions higher than 3. All of our formulas that we learned in our algebra classes so far just have n-dimensional analogs. So we know that the distance formula that you probably learned in your geometry class is just x1 minus x2 squared plus y2 minus y1 squared. This was on the xy axis, right? Guess what it is in 3 dimensions? All we have to do is just tack on. This should be a 1 and this should be a 2, sorry. All we have to tack on is z1 minus z2 squared. That's it, because now we just have another dimension. So this is a very crucial formula. This is how to find the distance between any 2 points in 3-dimensional space. And this is 1 and this is 2. I apologize for that. And another thing that's very much the same is that if you have a set of all points that are the same distance from some center point, you have a sphere. And the equation of a sphere is using the distance formula is literally just x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared is equal to the square of the radius of the sphere. So this is the equation of a sphere in 3-dimensional space. And also it's very, very handy when doing equation of the sphere in 3-dimensional space is the midpoint formula. x1 plus x2 over 2, comma y1 plus y2 over 2, comma z1 plus z2 over 2. And this would give you the midpoint between the points x1, y1, z1 and x2, y2, z2. So yeah, this would help you find the center points, for example, to find the equation of a sphere. So let's do some practice now, knowing those. So say I have the point in 3-dimensional space, A, which is 4, 1, 5, and the point B, which is 8, 2, 6. And I want to find the distance between A and B. So go ahead, give that a try. Okay, so let's give this a go here. It's a big square root, and we would have to do 8 minus 4 squared plus y2 minus y1, 2 minus 1 squared plus 6 minus 5 squared. And this FYI, if you did 4 minus 8, that's fine because we have a square here, and that wouldn't break any that wouldn't break math in any way because we're going to have all positives under the square root. So just continuing our arithmetic now. We have 4 squared, which is 16, plus 1 squared is a 1, plus another 1 squared is just a 1, which gives you the square root of 18. If you want to simplify this, break the radical up into 9 times 2. And square root of 9 is 3, so we get 3 times the square root of 2 units as our final answer. That's how far apart these points are in 3-dimensional space. So let's do one more, just for practice sake. And let's say we have the point, give me a second, 0, 2, 4. And the point Q, which is the point 3, 2, 8. And we want to find the distance between P and Q. Let's give that a try. Well, once again, we're going to do a big square root. 3 minus 0, because it's y2 minus y1 squared, plus 2 minus 2 squared, plus 8 minus 4 squared, and what do we get now? We get a 3 squared, which is a 9, plus a 0 squared, which is a 0, and a 4 squared, which is a 16, and lo and behold, we get a perfect square, which is just 5 units. Make sure, I don't know how picky your professor or teacher could be, but just always when you're doing distance measurements, just always make sure to put units. So now let's use our midpoint formula first before we were to use find the equation of a sphere. So let's say we have the point 4, comma 0, comma minus 6. That's a 0. I apologize. Then we have another point given by 8, 8, and 20. And I want to find the midpoint between these 2 points. I want to find a point such that the distance from that point to each side is the same. I want to find the middle of a line that's connecting them. So to do this, remember our formula from before. It's just as simple as just adding up these two and dividing by 2, adding these two up and dividing by 2, and adding the z components up and dividing by 2. So the midpoint would be 4 plus 8 over 2, comma 0 plus 8 over 2, comma minus 6 plus 20 over 2, which is 12 over 2 is a 6. 8 over 2 gives you a 4. And 20 minus 6 is a 14 over 2 is a 7. So this would be the midpoint between these 2 points. And you can verify this. Just go onto a graphing software and punch in these numbers. One that I like to use is GeoGebra. I'll link it in the description below. So now that we know how to use the midpoint formula, let's find the equation of a sphere with its center at 7, 1, minus 2, and with a radius of 1 unit. So go ahead, if you want to be ambitious, give this a try. So I already showed you the equation of a sphere, and literally all you have to do is just plug in the center and the radius. So it would be x minus 7 squared plus y minus 1 squared plus z minus 2 gives you a plus 2 is equal to our radius squared, which is 1 squared is a 1. So if you were to put this into that graphing software, GeoGebra, you would get a 3-dimensional sphere with the center at 7, 1, minus 2, and its radius would be 1. So that was kind of an easy one. Let's do a little bit more harder example. Say I give you that the endpoints of a diameter on some 3-dimensional sphere in space, obviously, is given by 2, 1, 3, and the point 1, 3, minus 1. So now, find the standard equation of this 3-dimensional sphere. Well, first we have to find the center. And to find the center, and if we're given 2 endpoints of a diameter, we have to use the midpoint formula. Because the midpoint of 2 endpoints of a diameter must be the center of the sphere. So 2 plus 1 over 2, comma 1 plus 3 over 2, comma 3 minus 1 over 2. So essentially like finding the average, if you want to think of it like that. This would, of course, give us a 3 over 2, or 1.5. 4 over 2 is a 2. 2 over 2 is a 1. So this would be our center. And there's one more piece of information that we need in order to build our equation. We could do this 2 ways, actually. We could find the distance between these 2 endpoints, and that would give us the diameter of the sphere. So we'd have to half that and then square it to get r squared. Or we can find the distance between here and the center, which just gives us r. So I'm going to do that way. So I know that r must be given by 3 over 2 minus 2 squared plus 2 minus 1 squared plus 1 minus 3, it's a plus, minus 3 squared. Now let's calculate this. Don't get scared of any fractions. This is essentially 1.5 minus 2, which is just a 0.5, because I'm just going to say it's positive because we're squaring it. So 1/2 squared is 1/4 plus 1 plus 1 minus 3 is a -2. -2 squared is a 4. And adding these up now, this is 4 over 4 and 16 over 4. So 16 plus 4 is a 20, 21, 21 over 4. Let me just make sure I did that right. 21 over 4, right? This is a 4 over 4. Yep, 21. Okay. And if we want to try and simplify this, it could be the square root of 21 over 2. That's what r is. So let's just do a quick summary of everything that we know so far about the sphere. I know the center point and I know the radius. And that's literally all we need. That's all the standard equation of a sphere requires us to know. So here's a bit of a drum roll here. Let's see here. Now it is finding the equation of a sphere here is x minus 3 over 2 squared plus y minus 2 squared. I'm just taking from the center here. Plus z minus 1 squared is equal to, don't forget to square this. This is just r. So r squared would be 21 over 4. And this is our answer here. And if you want to check our answer, put these points into a calculator real quick. I'll do that. That's 2 minus 3 over 2 squared. Plus 1 minus 2. I probably could just do this in my head, but I'm a little lazy, sorry. 3 minus 1 squared. And sure enough, it is 21 over 4. So yeah, you could do that for the other diameter, but I'm very confident that we got the right answer. So this would be it. Now, we could just extend our notion of vector quantities now into three-dimensional space. It's literally the exact same thing. We're just tacking on an extra component, just the z component now. So let's say I have a vector in three-dimensional space with initial point P at -1 to -1, comma 2, comma 3. And I know that its terminal point is at 3, 3, 4. And I want to find the component form of vector PQ. So go ahead. I challenge you to give this a try. It's literally, don't be intimidated by it. All right, so literally we're just going to do what we did for the vectors in the plane. We're going to do 3 minus minus 1. Just subtracting the initial point from the final point. 3 minus minus 1. Now 3 minus 2, comma 4 minus 3. This was just the little addition point here. Now we're just tacking on another component. It's literally the same thing as before. And if this is a little foreign to you, just make sure to watch our videos on vectors in the plane and component form. Now I'm just going to do this arithmetic. 4, 1, 1. And this would be vector PQ. Now what if I asked you for the magnitude of vector PQ? How would you go about doing that? Well, this is essentially just, if you want to use the distance formula on P and Q, you'd get the same answer. That's literally just finding, squaring, and summing the components. So 16 over 4 squared plus 1 plus 1, which is the square root of 18. And if you want to simplify this, this would be just 3 times the square root of 2. And if you want to find the direction for PQ, remember our video from before, we could use an angle to do that. And we would find that, well, actually, there's one little difference here. It was easier for vectors in the plane. This time, we can specify direction just by looking at the component form. We know that it's 4, 1, 1, but there's also these things called direction cosines, which I'm going to get to in a later video. So let's hold off on the direction for now. But the way you find the magnitude is just using the distance formula. So let me just show you once again that we're doing the exact same thing for vectors in the plane. If I give you a vector v given by 2, 1, 3, and I want you to find 2v, how would you do that? Well, literally all we have to do is just tack on a 2 over here. And we're going to think of this as like distributing the 2 to every component inside. So now I get 2 times 2 is a 4. 2 times 1 is another 2. And 2 times 3 gives you a 6. So this vector over here would be the vector v scaled by 2. And sure enough, 4 by 2 is 2, 2 by 1 is 2, and 6 by 3 is 2. Now let's say I give you 3 vectors. First I give you u, which is 1, 2, 3. The vector v, which is 2, 2, comma, minus 1. And w, which is 4, 0, minus 4. And I want you to find vector z such that z is 5 u hat, oh not u hat, sorry, 5u minus 3v minus 1/2 of w. So go ahead, give this a try. Well, once again, to do this, we're going to just tack on some scalars to this. So I know z must be 5 multiplied by the vector 1, the vector 1, 2, 3 multiplied by a scalar multiple of 5, minus 3 times what v is, 2, 2 minus 1. I'm just pulling from over here. This is just 3 times what v is, minus 1/2 times 4, 0, minus 4. All right, so let's do this real quick. Distribute the 5 if you want to think of it like this. This would give us 5, 10, 15, minus, distribute that 3, 6, 6, minus 3. We're keeping the minus outside for now. Minus, distribute the 1/2, gives us a 4, 0, oh sorry, that's a 2, I apologize. Good thing I caught that. This should be a 2. So minus 2, 0, minus 2. And now we just combine the components. So we're going to combine 5, 6, and 2 in the way that we specify with the minuses. So this is 5 minus 6, which is a minus 1, minus 2. Minus 1 minus 2 is a minus 3. 10 minus 6 minus 0 is just a 4. 15 minus minus 3 is an 18. And then minus minus 2 is a 20. So this should be your correct vector. And there's one little other piece of knowledge that I forgot to talk about real quick. Let me just mention this. if you have two vectors, and of course, we'll call them u and v. Actually, you know what? Let's switch it up. Let's call them d and e. So let's say vector d is given by a scalar multiple of another vector, call it e. Then vectors d and e must be parallel. All e is doing is just getting scaled by it. And I could show this in, let me show this in 2 dimensions first off, rather than going to 3 dimensions really fast. So let's say we're in the xy plane, just to make a point here. And I have vector d. Actually, let's call this, this is vector. 1 minute. And let's make the other one in a different color. All right. So let's say that this is actually vector e, and the other guy is vector d. So looking at these, it looks as if e is like sort of 3/4 of vector d. So it's some kind of scalar multiple of d. And we could write that as like d is equal to some scalar multiple of e. And knowing this, all I did was literally just extend the length of vector e, and I got vector d. So if one vector is the scalar multiple of another vector, if d is equal to some constant multiplied by e, then vector d must be parallel to vector e. This is a very good thing to understand. Just if two vectors are scalar multiples of one another, they're said to be parallel. So for our final exercise, I'm going to give you vector z, which is given by 1/2 I hat minus 2/3 j hat plus 3/4 k hat. And I'm going to give you another one just by 6 I hat minus 4 j hat plus 9 k hat. And I want you to determine if these two vectors are parallel or not, using what I just told you. So the key thing that you have to do is to see if z is some scalar multiple of this vector. So let's see that. Let's see if 1/2 times some constant is going to give us 6. Well, this constant must be 12, sorry. And similarly, let's see if negative 2/3 times the same constant is equal to minus 4. So solving for c, I'm going to get negative 2c is equal to negative 12. So c must be equal to a positive 6. We get a different, these guys aren't equal. So I know that z could not be a scalar multiple of whatever this vector is. So therefore, you could say if you want, since there is no c such that c times z hat is equal to, I didn't give this a name, we'll call it a, is equal to a, we know that z hat must not be parallel to a hat. Oh, not hat, you know what I mean. But this is the key intuition, is that because they're not scalar multiples, they cannot be parallel to one another.